what I'm going to do is I'm going to explain to you an extreme green concept that was developed at NASA's Glenn Research Center in Cleveland, Ohio. But before I do that, we have to go over a definition of what green is, because a lot of us have a different definition of it. Green, the product is created through environmentally and socially conscious means. There's plenty of things that are being called green now. What does it actually mean? We use 3 metrics to determine green. The first metric is it sustainable? Which means, are you preserving what you're doing for future use or for future generations? Is it alternative? Is it different than what's being used today, or does it have a lower carbon footprint than what's used conventionally? And 3, is it renewable? Does it come from Earth's natural replenishing resources, such as sun, wind, and water? Now, my task at NASA is to develop the next generation of aviation fuels. Extreme green. Why aviation? The field of aviation uses more fuel than just about every other combined. We need to find an alternative. Also, it's a national aeronautics directive. One of the national aeronautics goals is to develop the next generation of fuels, biofuels, using domestic and safe, friendly resources. Now, combating that challenge, we had to also meet the big 3 metric. Actually, this is extreme green for us is all 3 together. That's why you see the plus there. I was told to say that. All right? So it has to be the big 3 at GRC. That's another metric. 97% of the world's water is salt water. How about we use that? Combine that with number 3. Do not use arable land, because crops are already growing on that land. That's very scarce around the world. Number 2, don't compete with food crops. That's already a well-established entity. They don't need another entry. And lastly, the most precious resource we have on this earth is fresh water. Don't use fresh water. If 97.5% of the world's water is salt water, 2.5% is fresh water, less than 0.5% of that is accessible for human use, but 60% of the population lives within that 1%. So, combating my problem was, now I have to be extreme green and meet the big 3. Ladies and gentlemen, welcome to the Green Lab Research Facility. This is a facility dedicated to the next generation of aviation fuels using halophytes. A halophyte is a salt-tolerating plant. Most plants don't like salt, but halophytes tolerate salt. We also are using weeds, and we're also using algae. The good thing about our lab is we've had 3,600 visitors in the last 2 years. Why do you think that's so? Because we are on to something special. So in the lower, you'll see the green lab, obviously, and on the right-hand side, you'll see algae. If you are into the business of the next generation of aviation fuels, algae is a viable option. There's a lot of funding right now, and we have an algae to fuels program. There's 2 types of algae grown. One is a closed photobioreactor that you see here, and what you see on the other side is our species. We're currently using a species called Synodesmus dimorphus. Our job at NASA is to take the experimental and computational and make a better mixing for the closed photobioreactors. Now, the problem with closed photobioreactors are they're quite expensive. They're automated, and it's very difficult to get them in large scale. So on large scale, what do they use? We use open pond systems. Now, around the world, they're growing algae with these racetrack designs that you see here. It looks like an oval with a paddle wheel. It mixes really well. But when it gets around the last turn, which I call turn 4, it's stagnant. We actually have a solution for that. In the Green Lab, in our open pond system, we use something that happens in nature, waves. We actually use wave technology in our open pond systems. We have 95% mixing, and our lipid content is higher than a closed photobioreactor system, which we think is significant. There is a drawback to algae, however. It's very expensive. Is there a way to produce algae inexpensively? And the answer is yes. We do the same thing we do with halophytes, and that is climatic adaptation. In our Green Lab, we have 6 primary ecosystems that range from freshwater all the way to saltwater. What we do, we take a potential species, we start at freshwater, we add a little bit more salt. When the second tank here will be the same ecosystem as Brazil, right next to the sugarcane fields, you can have our plants. The next tank represents Africa. The next tank represents Arizona. The next tank represents Florida. And the next tank represents California or the open ocean. What we're trying to do is to come up with a single species that could survive anywhere in the world where there's barren desert. We're being very successful so far. Now, here's one of the problems. If you are a farmer, you need 5 things to be successful. You need seeds, you need soil, you need water, and you need sun. And the last thing that you need is fertilizer. Most people use chemical fertilizers. Well, guess what? We do not use chemical fertilizer. Wait a second. I just saw lots of greenery in your green lab. You have to use fertilizer. Believe it or not, in our analysis of our saltwater ecosystems, 80% of what we need are in the tanks themselves. The 20% that's missing is nitrogen and phosphorus. We have a natural solution. Fish. No, we don't cut up the fish and put them in there. Fish waste is what we use. As a matter of fact, we use freshwater mollies that we've used our climatic adaptation technique from freshwater all the way to seawater. Freshwater mollies, cheap. They love to make babies. And they love to go to the bathroom. And the more they go to the bathroom, the more fertilizer we get, the better off we are, believe it or not. It should be noted that we use sand as our soil, regular beach sand, fossilized coral. All right, so a lot of people ask me, how did you get started? Well, we got started in what we call an indoor biofuels lab. It's a seedling lab. We had 26 different species of halophytes, and 5 are winners. What we do here is it should be called a death lab because we try to kill the seedlings, make them rough. And then we come out to the green lab. What you see in the lower corner is a wastewater treatment plant experiment that we're growing a macroalgae that I'll talk about in a minute. And lastly, it's me actually working in a lab to prove to you I do work. I don't just talk about what I do. All right, here's a plant species, Salicornia virginica. It's a wonderful plant. I love that plant. Everywhere we go, we see it. It's all over the place, from Maine all the way to California. We love that plant. Second is Salicornia beglovi, very difficult to get around the world. It is the highest lipid content that we have, but it has a shortcoming. It's short. Now you take Europea, which is the largest or the tallest plant that we have, and what we're trying to do with natural selection or adaptive biology, combine all 3 to make a high-growth, high-lipid plant. Next, when the hurricanes decimated the Delaware Bay, soybean fields, gone. We came up with an idea. Can you have a plant that has a land reclamation positive in Delaware? And the answer is yes. It's called seashore mallow. Cutzkalutskia virginica. Say that 5 times if you can, fast. This is a 100% usable plant. The seeds, biofuels. The rest, cattle feed. It's there for 10 years. It's working very well. Now we get to Catamorpha. This is a macroalgae that loves excess nutrients. If you're in the aquarium industry, you know we use it to clean up dirty tanks. This species is so significant to us, the properties are very close to plastic. We're trying right now to convert this macroalgae into a bioplastic. If we are successful, we will revolutionize the plastics industry. So, we have a seed to fuel program. We have to do something with this biomass that we have. And so we do GC extraction, lipid optimization, so on and so forth, because our goal really is to come up with the next generation of aviation fuels. Aviation is specific, so on and so forth. So far we've talked about water and fuel. But along the way, we found out something interesting about Salicornia. It's a food product. So we talk about ideas worth spreading, right? How about this? In sub-Saharan Africa, next to the sea, salt water, barren desert? How about we take that plant, plant it, half used for food, half used for fuel? We can make that happen inexpensively. You can see there's a greenhouse in Germany that sells it as a health food product. This is harvested. And in the middle here is a shrimp dish, and it's being pickled, so I have to tell you a joke. Salicornia is known as sea beans, saltwater asparagus, and pickleweed. So we're pickling pickleweed in the middle. Oh, I thought it was funny. And the bottom is Siemens mustard. It does make sense. This is a logical snack. You have mustard, you're a seaman, you see a halophyte, you mix it together, it's a great snack with some crackers. All right? And last, garlic with salicornia, which is what I like. All right? So, water, fuel, and food. None of this is possible without the Green Lab team. Just like the Miami Heat has the big three, we have the big three at NASA GRC. That's myself, Professor Bob Hendricks, who's our fearless leader, and Dr. Arnon Chait. The backbone of the Green Lab is students. Over the last 2 years, we've had 35 different students from around the world work in the Green Lab. As a matter of fact, my division chief says a lot, you have a green university. I was like, I'm okay with that, because we're nurturing the next generation of extreme green thinkers, which is significant. So, in first summary, I presented to you what we think is a global solution for food, fuel, and water. There's something missing to be complete. Clearly, we use electricity. We have a solution for you. We're using clean energy sources here. So, we have 2 wind turbines connected to the Green Lab. We have 4 or 5 more hopefully coming soon. We also are using something that's quite interesting. There is a solar array field at NASA's Glenn Research Center. Hasn't been used for 15 years. Along with some of my electrical engineering colleagues, we realized that they're still viable. So we're refurbishing them right now. In about 30 days or so, we'll be connected to the Green Lab. And the reason why you see red, red, and yellow is a lot of people think NASA employees don't work on Saturday. This is a picture taken on Saturday. There are no cars around, but you see my truck in yellow, so I work on Saturday. This is proof to you that I'm working, because we do what it takes to get the job done. Most people know that. Here's a concept with this. We're using the Green Lab for a microgrid testbed for the smart grid concept in Ohio. We have the ability to do that, and I think it's going to work. So, Green Lab Research Facility, a self-sustainable renewable energy ecosystem, was presented today. We really, really hope this concept catches on worldwide. We think we have a solution for food, water, fuel, and now energy. Complete. It's extreme green, it's sustainable, alternative, and renewable, and it meets the big three at GRC. Don't use arable land. Don't compete with food crops. And most of all, don't use fresh water. So I get a lot of questions about what are you doing in that lab? And I'll usually say, none of your business. That's what I'm doing in the lab. And believe it or not, my #1 goal for working on this project is I want to help save the world.